We depend entirely on refined fuels to keep planes in the air, trucks on the highway, and the modern world moving. But if you pull a barrel of raw crude oil straight out of the ground, it is physically useless on its own. That is because raw crude is a chaotic, dirty cocktail. It is a tangled mess of paraffins, naphthenes, aromatics, sulfur, and even sand. Whether the oil is incredibly dense or highly fluid, sweet or sour, a refinery has one core objective. It has to untangle all of these specific microscopic compounds. You cannot simply pour raw crude into an engine and burn it. Its utility is only established after engineers systematically break it down and reverse engineer its chemical chaos. The very first roadblock engineers hit is physical corrosion. If you pump raw crude directly into a 400°C furnace, the trapped salt water and metals inside the oil will trigger severe pipe corrosion and rapidly foul the equipment. To get around this, refineries use a specialized workaround known as electrostatic desalting. First, they wash the raw crude with a continuous stream of hot water, usually making up about 3 to 10% of the total volume. This water dissolves and captures the harmful solid salts, like sodium chloride and magnesium chloride. Next comes the electrical step. This diagram shows the cross-section of a desalting tank, specifically highlighting the water-crude interface. Applying a high-voltage electrostatic field across those horizontal electrodes forces the microscopic water droplets to coalesce. They become heavy and drop out of the oil. By completely removing the salt and water up front, engineers solve the corrosion threat, yielding a clean, prepped crude that can actually survive the intense heat of the primary separation phase. Now the refinery faces a massive logistical challenge, finding a way to sort thousands of distinct hydrocarbon molecules without having to pick them apart one by one. The solution relies on a fundamental thermodynamic principle. As this animation demonstrates, smaller, lighter carbon chains boil at much lower temperatures, while the longer, heavier chains require higher heat to vaporize. To execute this, engineers heat the crude to nearly 400°C, injecting the resulting vapor into a massive atmospheric distillation column, towering 50 meters. On this blueprint, vapor naturally sorts itself. At the top, light fractions like naphtha condense below 160 degrees. In the middle, at higher temperatures, medium distillates like jet fuel and diesel condense. Down in the lower section, heavy gas oil is extracted. Heat successfully sorts the oil by size, but leaves behind a stubborn pool of highly valuable sludge, requiring a completely different engineering approach. This atmospheric residue pooled at the bottom contains some of the most lucrative lubricating oils in the entire barrel. The problem is, they simply will not boil at 400 degrees. Engineers hit a hard thermal limit here. If they try to extract these oils by heating the residue past 450 degrees, the molecules undergo thermal cracking. They break down into hard, solid coke, which instantly destroys the internal equipment. Instead of raising the heat, engineers use an ingenious physics hack. Liquids boil rapidly at lower temperatures if you remove the atmospheric pressure around them. Using high-speed steam ejectors, engineers drastically lower the pressure inside a stubby vacuum tower to between 10 and 30 millimeters of mercury. This extreme vacuum allows the heavy vacuum gas oil and lube bases to boil off without destroying their long, complex chains. By manipulating the pressure instead of fighting the temperature limit, the refinery rescues high-value bases from what would otherwise be useless sludge. The final hurdle is matching the oil to the market. Looking at this breakdown of a typical barrel, the natural proportions of separated crude yield far too much low-value heavy oil and nowhere near enough high-demand, high-octane petrol. To fix this, engineers act as molecular alchemists in a process called fluid catalytic cracking. They apply 530-degree heat and specialized catalysts to violently snap the heavy gas oil chains into smaller petrol molecules. They also use catalytic reforming to reshape the molecules. Straight carbon chains are physically folded into hexagonal aromatic rings, improving the fuel's quality. Finally, in a purification step called hydrotreating, high-pressure hydrogen is pumped in to strip out the very last traces of toxic sulfur before the finished fuel is sent to market. These cracking and reforming stages move the refinery's role from sorting to manufacturing. Engineers actively rewrite the molecular anatomy of the oil to force the yield to match the specific volume and quality required by the market. This complex flow sheet charts the complete chemical journey: desalting, thermodynamic sorting, and extreme molecular restructuring all act in concert to maximize the value of every single carbon atom. The ultimate payoff of this engineering gauntlet is the creation of the refined jet fuel, diesel, petrol, and asphalts that we consume daily. The modern oil refinery is a triumph of problem solving, a facility that systematically exploits the laws of thermodynamics to produce the specific fuels required to keep civilization running.